Last up for this worksheet is topic 3, where we're going to talk about solving systems of linear equations where you have no solution or infinitely many solutions. So we do have some definitions that we need to go over. The first is a system of linear equations with at least one solution is called a consistent system. So the systems of equations that we have looked at so far in this worksheet have all been consistent. They had that one solution, okay? Now on the flip side of that, a system of linear equations with no solution is called an inconsistent system. So let's think about that. If you have no solution, and we know that the solution is the point of intersection, a system that has no solution would be two lines that never intersect, okay? So to have no solution, you couldn't intersect. That would be two equations that are parallel. So a system that is made up of two parallel lines would end up being an inconsistent system. There would be no solution because those two lines are never going to intersect. Okay? And then finally, a system of linear equations with infinitely many solutions is made up of two equations that graph the same line. So sometimes you'll have two equations that maybe on the surface look different, but when you really break them down, you realize they're the exact same equation and they graph the same line. Equations like that are called dependent equations. Even though the equations on the surface look different, they graph the same thing. Okay, so you have a consistent system, at least one solution, inconsistent system, no solution, made up of parallel lines. Then you have this weird type of system where you have two equations that graph the same thing, and those equations are called dependent equations. So let's look at an example of each. Okay, now on the surface, these equations look fantastic. They don't look weird at all. They look totally normal. But if you take some things that you already know, you can figure something out, especially about part A, very, very quickly. So example 3 says solve each system of linear equations by graphing, okay? Well, if you look at part A, we have y equals 3x minus 1 and y equals 3x plus 2. So let's look at the parts of these two equations. So I've been using the red and purple theme, so let's keep that going. So for this first equation, the slope is 3 and the y-intercept is -1. For the second equation, the slope is also 3, but in this case, the y-intercept is 2. And if we go back to when we were first learning about parallel lines, we found out two very important details about parallel lines. Number one, they have the same slope. Number two, they have different y-intercepts. And that is exactly what is happening here, okay? But let's go ahead and graph these two lines and just see what's happening. So let's go back to red. We'll graph the red equation first. So we want to plot the y-intercept first, okay? So the y-intercept here is really 0, -1. So at the origin, I don't go left or right, but I do go down 1. And then I want to go up 3 to the right 1. So remember, this right here is the same as 3 over 1. So I'm going to go up 1, 2, 3 over 1, up 1, 2, 3 over 1. I could also do the exact opposite of that, and instead of going up, I could go down, but instead of right, I would have to then go left. So I could go down 1, 2, 3 to the left 1, down 1, 2, 3 to the left 1. You need at least 2 points for a line, so you really only have to apply the slope once, but sometimes it's nice to apply it a few different ways, or a few different times rather. So now we connect and pretend this line is straight as an arrow, okay? Pretend I drew it just absolutely perfect, okay? This is the risk of graphing systems of equations. We have a little bit of user error when we graph by hand. Okay, second equation. Let's look at the second one. So for the second equation, we have a y-intercept of 2. So at the origin, I don't go left or right, but I do go up 2. And then I need to apply my slope, which again is 3 over 1. So I can go up 1, 2, 3 over 1, up 1, 2, 3 over 1. I could go down 1, 2, 3 over 1. I could go down 1, 2, 3 over to the left 1. And if you'll notice, these equations are for sure parallel. They will never intersect each other. And pretend the lines are perfect. My lines are a little wonky, but if you graph this just so, you can see that these are for sure parallel. And let's go ahead and jump over to Desmos just so you can see it with, a slightly more precise graph, okay? So let's see Desmos. I think I have it right here. We want to look at Desmos. Okay, so the first equation of that system was y equals 3x minus 1. And the second equation was y equals 3x plus 2. And there you can see it here. These two lines with, a steady hand will say this is drawn, very precisely. We can zoom out and zoom out and zoom out, and these lines never intersect. Okay, so you can see here for sure, without a shadow of a doubt, you've got a set of parallel lines. They're never going to intersect. Okay. All right, let's go back to the worksheet. Okay, so in this situation, we would want to say that these two lines are parallel lines, and there is no solution. We could also say that this is an inconsistent system. There's no solution to it. Okay, now finally down here, for part B, we have y equals 2x minus 4, and then we also have 4x minus 2y equals 8. So let's look at the first equation in red. So the slope of the first equation is 2, or we can say 2 over 1. The y-intercept of the second equation is negative 4, and remember that could also be written as 0 minus, or 0 comma negative 4. Okay, first equation was super easy. It was in slope-intercept form. So let's go ahead and graph this. We want to plot the y-intercept, which is negative 4. So at the origin, I don't go left or right, but I do go down 1, 2, 3, 4. And then from there, I can go up 2 to the right 1, up 2 to the right 1. If I wanted to get wild and crazy, instead of going up and to the right, I could go down and to the left. So I could go down 1, 2 to the left 1, down 1, 2 to the left 1. Either way, plot, connect, don't forget your arrows, okay? Now, the second equation, we're going to have to do a bit more work. We have 4x minus 2y equals 8. We need to go ahead and solve this for y. That's a nice, easy way to graph. So I'm going to start by subtracting 4x from both sides. 4x minus itself is 0. 0 minus 2y is negative 2y. And then on the right, I'm just left with 4x, or negative 4x plus 8. Now, in order to get the y alone, I have to undo the multiplication of negative 2 and y. So I'm going to divide all three terms by negative 2. So let's see, negative 2 divided by itself is 1. 1 times y is y. Negative 4 divided by negative 2 is positive 2. And then 8 divided by negative 2 is negative 4. So if we look at this line and we compare it to this equation right here, even though on the surface these look like two completely different equations, now that we've solved the second equation for y, we can see that they're exactly the same. They have the same slope, they have the same y-intercept, so if I were to graph them, I would get all the same points. And so we can see now that we have dependent equations. These two equations, while on the surface look different, they really graph the exact same thing, okay? So we can jump over to Desmos really quick and look to see what's happening there. So the first equation we had was y equals 2x minus 4. And the second equation we had was 4x minus 2y equals 8. And you can see now there's no differentiation between the two lines. These two equations really truly graph the same exact line. So in terms of the solution here, when we're looking for solutions to a system, we're looking for the point of intersection. Well, these two equations, they intersect everywhere. Every single ordered pair that satisfies one equation is also going to satisfy the other equation. So we need to talk about what that is going to look like for us. So we do need to indicate to the reader that we have infinitely many solutions, okay? So infinitely many solutions. And I don't want to say infinitely many solutions and just be like too vague with it. It's not that all real numbers work, so do not ever put all real numbers here. The solutions to systems of equations are not just real numbers, they're ordered pairs. So we want to say infinitely many ordered pair solutions, but it can't just be any old order pair. Okay, you can't just be like, oh, it's any ordered pair. No, 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 no. It's very, very specific ordered pairs, and we have a very specific kind of wacky way we write that. So we're going to use something called set notation. You start with curly braces, and you want to indicate the type of solution that you have. Okay, now you've seen set notation before when we talked about linear inequalities in one variable. Well, it's back. So here we want to state the variable or state the type of solution. So in previous videos, we talked about stating the variable. We were looking for values for x such that. Well, now we're not just looking for single values for x. We're looking for ordered pairs. So the type of solution we're looking for is ordered pairs. So just state a very generic XY ordered pair and then put this vertical line. This vertical line says that we're looking for ordered pairs such that, and then just state one of those two equations. So we're looking for ordered pairs such that y equals 2x minus 4 is satisfied. So this basically tells the reader we're looking for all of the ordered pairs that satisfy this equation. If they satisfy this equation, they're obviously going to satisfy the other equation. So wacky notation here, but hopefully it kind of makes sense to you. Again, we're not looking for just values for X or Y. You cannot say all real numbers. We're looking very specifically for ordered pairs and very specifically ordered pairs that satisfy a very particular equation.